Quiet, Cyrus. All right, hello everybody. Welcome back to the afternoon session of HATRA. This is the interactivity and visualization for programmers session. And first up, I have a slight conflict of interest. We have debugging trait errors as logic programs presented by Gavin and co-authored by me.
Thank you for the very warm welcome, Will. Yes, so my name is Gavin Gray. I'm a master's student at ETH Zurich. Today we're going to be talking about trait errors. Of course, this is going to be a little bit related to Rust. Will is on the paper. And the reason that we're talking about them is traits are used for lots of crazy things, sometimes abused. So in the top, we have the fourth programming language. This is used in a macro, and it compiles into a series of traits which are run at compile time. In the bottom right here, we have a maintainer of a large library, and they are in the GitHub discussions admitting that previous iterations of the library actually crashed the Rust compiler because they sort of are abusing some of the type safety that traits give them. And in the bottom left, we have a very readable and easy to look at type declaration. Everything there is a type, and for the rest of the presentation, hopefully you don't have to look at that. So we're going to try and get away from it. But the important thing here is that all of these are complex, and the compiler is trying to give diagnostics for these things when something goes wrong. And diagnostics also don't give us the most information. And we're going to be looking at why and sort of our proposal for a solution. But first, let's do a quick run through of what traits sort of look like in Rust and why they're important in this case. So here we're defining an into string trait, and this is establishing sort of a unit of shared behavior. If you're familiar with Haskell type classes or even interfaces in Java, this should be a familiar concept to you. Then in Rust, we can associate a type with a given trait. So here on the left, we're implementing our into string trait with the type tuple of integer. Now on the right, I have written this in sort of a pseudo-logical syntax. So this is declaring a fact that the type tuple of integer does implement into string. That's a fact that we give the compiler. And this sort of logical notation gets rid of a lot of the other cruft, for example, the method implementations for the trait. We're only caring about the types and the traits involved. The next type of definition we have is a parametric implementation. So here we're associating the type vector of t with the into string trait. But it's parameterized over type t, and we are also saying that t has to satisfy some condition. That's what this funny little t syntax is saying, well, the elements of t, the type of those elements, also need to implement into string. And so then vectors of those elements implement into string, but vectors of elements whose types do not implement into string don't work. And in the logical syntax, this corresponds to a rule. So, familiar, we say vector of t implements into string. That's the consequence, but the condition is that t has to implement into string. Then at the bottom, we have some client code. We're constructing a vector of tuples of integers, and we're calling toString on v. And so in order to type check this, the compiler is going to look at the type of v, and it's going to query sort of the facts and the rules that we've built up, and it's going to ask, does a vector of a tuple of integers, does that implement into string? And so we're going to go through sort of what the type checker does, and we're going to trace it in a Prolog-esque fashion. Been presenting these rules and facts in this Prolog notation, and we're going to stick to this relationship between Rust traits and Prolog. So we're asking the question, does a vector of tuple of integers implement into string? Then we come across the rule that says, well, yes, if the elements of that vector implement into string. So the type checker will sort of unify that variable t with our tuple of integers, and this condition is now pushed onto our search tree. We then later come to this fact in our database that a tuple of integers does indeed implement into string, and therefore the answer is yes, this is a well-formed and well-typed expression. We, of course, care about the cases when things go wrong. So let's modify our client a little bit. We are now constructing a vector of strings, and the query that the type checker now runs is, does a vector of string implement into string? And we can, of course, go through the same steps. So we start out with the same query at the top, vector string implementing into string. The compiler then finds that rule, tries to use it, and then it has the condition that string has to implement into string, which, funnily enough, it does not in our code. So the answer is no. And this is a type error. And how Rust presents this type error to the user is really important. And in this case, I claim that it is a good error. So at the top, it's telling us that, vector string, you can't call toString on that. That's good. That's sort of the high-level error. Down a little bit, it gives us these notes. It says, well, string doesn't implement into string, and vector string doesn't implement into string, and then ultimately, this is sort of the root cause of our problem, why the program doesn't compile, is that string doesn't implement into string. And at the bottom, it even gives us provenance. So it highlights the rule in the code, that parametric implementation. It highlights that and tells us this is where that string condition came from. That's why string has to implement into string. This is, of course, a smaller program than you would find in the wild or write yourself. And we care about, in the ecosystem, the libraries that use traits quite heavily and how this interacts with diagnostics. So, these are all examples of libraries that use traits heavily, and we're going to be focusing on one in the area of game development, just because of our familiarity with it. And it's called Bevy. And one of the funny things about Bevy is that it touts that it is a refreshingly simple data-driven game engine, but we want to inspect this simplicity. Does this claim really hold? This is a hello world example from sort of the Bevy documentation. So the model of Bevy is that there exists a world, and inside that world there are resources. We then define these functions. These are called systems, and a system takes in as a parameter a resource from the world, and then it can act on that resource. So you might have a player, you move their position. In this case, we have a timer, so we're declaring that resource here, and then we have this system run timer, which in theory could just increment the timer. And this code is good. This code runs, is perfect, not a very exciting game, but you can run it. If we modify the code to reflect a common user error, so you might not have seen it, in that middle, we're removing the little res wrapper around timer. And the problem here is that timer alone doesn't implement a trait bound called system param, but a res of timer does. So we would hope that the diagnostic would tell us, well, timer doesn't implement system param, but if you take res of timer, it might. Timer nor system param is mentioned in the about 30-line diagnostic. So that's a little disappointing. This is the diagnostic. Please don't read it. But we will look at it a little bit later. But the point is that it's long and I think a little confusing, but none of the information we really care about is in that diagnostic. And we want to know why and how we can get over this gap. The first thing is documentation, right? We provide developers documentation. They should read it to understand our libraries and how to use them. But for this specific error, the information spans across 3 pages, and there are 92 trait implementations on those pages. Trait implementations that look like this. This is 1 1/4, and there's 92 of them. But in the actual error message, there's only about, in the error that we create, there's only about 6 relevant of these implementations. So the developer now needs to sift through all of this information and try and find what is really relevant to the core cause. And unfortunately, the compiler wasn't providing that information. So we're going to play the same game that we did before with our simple example, and we're going to trace the type checker and see what things it touches when trying to, see whether or not we have a well-formed system. I have translated the Bevy library into a series of logical clauses. Again, don't read them. We'll step through them one by one. But the main thing is that we have our function, which has a single parameter, timer, and we want to know if this implements into system. And so that's the top of our search tree. We then have these 2 rules. And it says, well, we can implement into system in one of 2 ways. It can be something called an exclusive system param function, or it can be a system param function. If we look at the exclusive system param function, this is only implemented for functions whose first argument is the world. Our function takes a timer, so those types aren't equivalent, and so the answer is just no. We then sort of backtrack and look at the other alternative in this tree, and we are trying to implement, system param function. And we find this rule that says it is implemented for functions of a single argument, and that argument has to implement system param. If we look at the rest of the facts in our database, we see that timer is a resource, and system param is implemented for resources that are wrapped in that res, but timer itself does not implement system param, and so the answer is no. And this is why we get the type error. Comparing these two side by side, hopefully there is sort of something obvious. In the top case, we don't really have a tree, we have a stick. And so the compiler can look down this linear set of conditions and say, okay, well, string doesn't implement into string, that's definitely the problem. So we'll talk about that in the diagnostic. In the bottom case, we have this branch. And the branching point is whether our function implements into system. And in this diagnostic, into system is the only trait that they talk about, because the compiler will not go below that branching point. It isn't going to try and infer what the developer meant. It could have meant, they could have meant an exclusive system param function or system param function. It's not going to guess for you, so it's just going to talk about into system and leave you to sort of do the guesswork yourself. And this is, fine. We have one branching point. We could, in theory, propose both of the solutions to the user, and they could then analyze each individually. But as I tried to allude to before, traits are really a Turing-complete language. And debugging a trait error is debugging an arbitrary program. And the compiler is trying to do this with heuristics. So we've been looking at this single case in isolation, but really there's a whole ocean of these cases where we have a heuristic, it fails, and so we're playing this game of heuristic whack-a-mole. One brief example is that you can get an overflow in the type checker trying to evaluate a condition. And this is essentially an infinite loop in a Prolog program. And this is just one other case where you have really arbitrary programs written into this type system. That's not great. And we view this as an interface problem. The compiler is trying to diagnose these with heuristics, thinking what is most probable, but we see this as the compiler has lots of information, and we should present this to the user in some way that they can look at it themselves and find the root cause. I think it's time for a demo. We're talking about all this visualization stuff. That is really small text. Let's go ahead and try and bump this up a little bit. So on the left, this is the same Bevy code that we saw before in Rust. And it has the error, right, where we have a function with timer, it's not wrapped in that res. And on the right, we have traced the type checker's execution. And we see, it starts out with something called into system config, which I didn't tell you about, but it's there. And then it has a single condition that, run timer has to implement into system of unit question mark. That question mark is just the type that the compiler could not infer. In sort of an ideal system, this would be source mapped, back to the source code and give you that type parameter source syntax, but in this fast demo, it's not there. But we do see the same structure. So we see here that it asks whether or not run timer does implement an exclusive system param function, and then the subcondition here that it has to be a function that takes in a reference to the world. And on the other side, we see that it's trying to implement system param function. It does have, in sort of the Prolog-like fashion, this branch that unifies the first argument in our function to a type of timer, but then ultimately it comes here and asks, does timer implement system param? And the answer is no. And this tree view is, fun, and it's fun to look at. I like pictures, but it's also kind of a tedious way to get your information, especially if you have, trait programs that are huge with 92 implementations on things. So we have sort of these alternative views that we're trying to think about. In this case, this is sort of a directory-style notation where you can step down the conditions, and if my screen were wide enough, you would get them on the same line. But you can ultimately go ahead and see, okay, that one doesn't work, and also we come down this way, and timer doesn't implement system param. An even more alternative view is we can invert the tree. So instead of going top down, we can see, okay, what are the leaves that failed? Present those first, and then users can traverse back up to the root of the tree and find sort of the sequence that got them here. And this is sort of gives you the most relevant information. It says, timer doesn't implement system param, and run timer is not of this type. And timer implementing system param is the information that we were actually looking for. Now I need to find my slides again. So that's a brief demo of sort of the pre.00001 implementation of this interface that we might give to people to diagnose these type errors. But there's also lots of other data that the compiler has. So here's a nice tweet of somebody saying, did Rust just write my type name to a file because it was too long? And the answer is yes, it does this a lot. Types get really large. I'm not even going to bother trying to tell you what this type is at the bottom because it goes on for a really long time. But we can think about presenting this information to a user in sort of an incremental fashion. So we can abstract away some of those generic parameters. In this case, we have a load query and a select statement. This is for a SQL library. And then we can give users the option to sort of look into that information as they might want to. So they can incrementally look at stuff, and maybe they see already, oh, well, this doesn't really look like the type I wanted it to, so I need to figure out why this is in this shape. So hopefully I have told you about Rust types and presented sort of their strong relationship to a logical system. We talked about a little bit the way in which we would give people an interface to search for the different constraints that are involved in their types. We also talked about sort of in this middle part how we might be able to abstract more data and give it to people in an incremental fashion. And we ask you, the HATRA community, the human aspects people, how would you design a trait debugger? Like, am I taking this from the wrong direction? Are there other related problems where this approach could be useful? I was talking to someone recently about debugging cock tactics, which shares a lot of similarity. And then also, if you were to want to use a tool like this, what sort of features would you hope that this interface has? And I hope we can open up for discussion. Thank you for listening.
All right, we have time for some questions.
Thank you for the talk.
Thanks.
So you showed this idea of debugging a program. In a program, you often have comments. So you were sort of showing the implementations and constraints that come from directly the source code without putting them into context. And so first things that I would wonder is if you would be able to add comments to these implementations to show them alongside of what is actually going on in this tree view. And more specifically, I know that in the Rust compiler, there's the system of providing more helpful error messages for certain missing trait implementations. And my question is whether you looked into that and whether you want to generalize it, and you look very happy, so I guess so.
Thank you for the question. So yes, the interface, if I understood correctly, like if it can provide comments and such relating back to the source code, it would hopefully map everything to the source code. So it would show you where the subconditions came from, which of those implementation blocks it tried to use, even linking to things like documentation and saying, here's that implementation if you want to go look at it. Yes, the Rust compiler does have some internal things, and from what we have looked at, a lot of the direction the community is going in is giving mechanisms to library designers on sort of tailoring some of the error message that they get, but we want to think of this in a domain general way. We don't really expect that every maintainer is going to provide perfect annotations or even annotations if they have a small library, so we want something that works in the arbitrary case. Other questions? Yeah.
So here you're modeling the type checker as this evaluation of a logic program, right? And I don't know if it really works that way or it's just a useful model, but in either case, it tries to do some unification at the leaves where that question got replaced with a timer, and then that affected what later branches looked like, but only in the branch where it got unified, right? So I'm wondering if you have thoughts on what's a good way to express to the user that, okay, these unifications are applicable to this branch and they don't carry across, or what order, because I think running a logic program in your head is something we're not really used to doing because we don't work with logic programs that often. And I do think it is related to debugging cog tactics because often the unification fails at some point deep in the tactic, and that's not the error message you see.
Exactly.
So yeah, what are your thoughts?
Yeah, so the slides that I cut out are actually the large history of debugging prologue, which focuses on sort of how can we show the control flow and the unification between values and those different variables. I got rid of those slides, but we could do something very similar with this tree here. And context is another thing which we can talk about for a long time afterwards, like come see me. And I sort of forgot the last part of your question. If you want to just repeat it, or if there was one.
Which part?
I don't remember. I don't remember, but hopefully that answers your question. Sorry.
Okay, if you think of another one, you can ask a second
please
question.
This is neat, thanks. When I think about debugging, I think about kind of a sequence of backup plans. So like plan A is like, I really don't want to understand this. I just want to like fix it. And then when that plan doesn't work, you're like, okay, I'm going to have to like really understand what's going on. And when I say really understand what's going on, there are different sort of levels of commitment. Like the first level is like, okay, I'm going to go read the documentation and understand the model. And then there's like, oh, I'm going to go like browse the internet and understand sort of the edge cases for the model. And then eventually you get desperate and you're like, okay, I actually have to understand this thing. I'm going to read the source code, right? And so at some point, to debug your program, maybe eventually you end up reading the source code to the trait checker. And so I guess the question that I'm asking is, what abstractions do you want your users to develop regarding the trait analysis? And how will you align those abstractions with the debugger that you're providing? In other words, it doesn't really have to be a Prolog program if you can show them a Prolog program that is true to the actual analysis, and the Prolog program is easier for them to debug.
Yeah.
But maybe there are approximations that work in many of the cases, and so they don't really have to understand the entire trait inference algorithm in some cases. But then in other cases, maybe they actually do. So I don't know how you think about that range of options.
Yeah, so I guess like the first thing I would have to say is this is how the compiler works. So we are just tracing the compiler here. We aren't doing our own trait inference algorithm or anything else. One of the things that we had hoped with sort of that bottom-up view was presenting those leaves, which in my mind would be the most low-cost way of trying to find out what actually went wrong. So in that case, we get the information that a timer doesn't implement its trait bound, but there's also some other things that were there, but they're a little more bogus, or they would take more work to sort of get it to work, right? You'd have to change the entire type signature of the function, and so I would imagine that is some measure of how much cost it would take. We can also sort those things by some heuristic. I was talking about heuristics are bad, but we could use them to sort them in terms of like the most probable and give users a sense of where to start. Does that answer your question? Yes.
Hi, I was just nice talk, and I really do like your visualizations, and I'm sure they could work for more than Rust. But I kind of have to say, do we really want a Turing-complete trait system in our language? I mean, we're not at Popple, so I do think that is something we can discuss here.
It's a good comment. Unfortunately, I'm not the developer of Rust, and so I can't, get rid of the trait system, but it is something that we work with in a lot of languages, Haskell, Scala, OCaml, etc. So.
Yeah, I just wear a t-shirt.
Perfect.
So I really like this, taking the idea that these are logic programs literally instead of just that happening to be how we tend to abuse these systems. Have you thought about there are other executions for logic programs like Datalog that's a little more forward-facing, so you could pose, questions of, here are the things we can conclude about this type, and then you can, maybe mix forwards and backwards kinds of reasoning there?
I have not personally thought about that. in a sense, no. My mental model has sort of been shaped by how the actual implementation of the trait system is, because we are trying to handle the entire domain of problems that people can write. But it would be an interesting thing to sort of think about. Thank you.
You can also not take it too literally, right? These are not logic programs. They are traits in Rust, and there is one specific limitations here, which is the orphan rule and this trait coherence system in Rust. So in particular, asking about features you might want in the system is when the search for some implementation is happening, you can restrict this based on which types exist in a module that cannot be implemented by the user, for example. Any thoughts on that?
Yeah, so thank you for mentioning coherence, because the implementation of this game library has to sort of get around coherence in some way, because orphan instances are disallowed in Rust. And so some of these peculiarities are sort of Rust specific in how the different constraints the language puts on it, but we go off of what the type checker does.
I want to emphasize one thing for clarity is, I think there's a bit of confusion about is Prolog really in the Rust compiler? And I think it is useful to think about as yes. There is literally a Prolog interpreter that is in the Rust compiler, and that these trait queries do literally become not strings, but basically Prolog programs. And because coherence, I'm pretty sure, gets enforced above that layer. So the trait solver is not aware of coherence. By the time it reaches that, it's just doing basically Prolog interpretation. And so we are presenting it that way. But that's, I just want to emphasize that we're not doing any interpretive work. We're not building a model and saying you could think about it like this. This is actually how it is. It's just not how the information is usually presented to Rust users.
Going back to the earlier comment about alternate ways that you could approach this problem of, you said that they're building a way to let library authors make annotations, which that was what I was originally going to ask about. I was like, oh, that sounds super cool. And the reason that I asked about this is because in my experience with Rust and with TypeScript, having recently written a really gross type hackery library in TypeScript, is that there's kind of cute libraries that use the language the way that it was maybe meant to be used, and then there's eldritch horrors, like the crates that you listed on your earlier slide. And I guess in my mind, my intuition is that you could just use Rust as it is for most of the crates, which are probably mostly going to be cute, and then put a little bit more library author effort into the eldritch horror ones like this, and then you should be mostly done. So I'd be curious if is there any related work on what percentage of libraries do stuff like this that needs this Esther work on top of it, or not?
So I don't know of any work that classifies or categorizes what percentage of the libraries use traits in this way. It is, there's enough of them that it comes up quite frequently on discussion boards, Reddit, Stack Overflow, things like that. And when people are trying to develop these, general libraries for game development or for web development or, SQL, object relational mapping, they rely on these things in order to be sort of simple and flexible while still getting that heavy static, type safety. So I guess the short answer is, I don't know.
So we should probably move on, but maybe as we're transitioning, I wanted to ask one question myself. This reminds me of Amy Coe's dissertation work, in which she looked at the problem of not only why did something not happen that you wanted to happen, and it seems like this is an instance of that. And I wonder, have you thought about proposing fixes or searching for fixes that would bridge that gap? Not just showing you the leaves of the tree, but how could we extend the tree maybe to make this happen? Because that's what the user actually needs to do.
Yeah, that is a really great. That's kind of makes me think of proof repair in a way of we have some proof tree and we need to repair it. I'm not a program synthesis expert. Maybe we'll tack that on to sort of the end of the project, but for now we're trying to focus on maybe the basics. But it's a good direction to extend to.
Yeah.
Thanks.
Cool. Well, let's thank our speaker again.